In this Part B lecture notebook for Module 3, we will understand and implement for and while loops in Python. We will also look at lambda functions, understand how to make lists using list comprehensions in Python, and create lists from a combination of lambda functions and for loops. The notebook contents at first appear rather brief in that we are just covering two basic ways of doing looping in Python, and there's one activity before the summary activity, but there is a certain amount of depth to these concepts, so you should take your time exploring these, even though the notebook itself is not very long. We begin with while loops. The syntax for a while loop is to write while, and then there's a condition that should be true, and then that allows you to enter this while loop, and then you'll do something cool. Maybe it's not so cool, it just depends on what you're actually asked to do in your code. And then you should be updating the condition or use break or continue to control what you're doing within your loop. As soon as you have no more indent, notice the indenting here, and of course this colon, all very important syntax. As soon as you get rid of the indent and continue to write your code, none of the stuff that is not indented in here will be part of the while loop. It'll just be executed after the while loop is completed. Here is an example of our very first while loop. We will set the variable a equal to 2. While a is less than 5, which is certainly a true condition, so it will enter into this while loop, we will simply print what a is, and this is definitely not a very cool thing to do, but we're just illustrating how this code works in terms of writing a while loop. We're illustrating the syntax, that is. And then we're going to add 1 to a and store that as a. So eventually this condition will become false, at which point it won't execute any of the contents within the while loop anymore because this will be false. As long as it's true, it will continue to do this. So if we go ahead and run this code, I'll just go ahead and do that now. You see that it prints 2, 3, and 4, and as soon as a is equal to 5, it's equal to 5, it's not less than 5, so that condition becomes false, and it didn't continue. Just to show you why the indenting matters, if you get rid of the indenting here, let's say I print hi right there, and I rerun this code, you'll see that hi is only printed at the very end. It was after this while loop was done executing, and then it went on to the next non-indented line of code to continue with what's ever going on in that code. Now, I could rerun this. Every time I run this code cell, I'm resetting a to be 2 on the first line of code. This condition is false, so this won't print anything. It never enters the while loop because the conditions for entering the while loop are false. So let's just go ahead and do this again, and you see nothing is printed at all. So the condition has to be true, and as long as it's true, you enter the while loop and you execute those commands. And the indenting is very important. If I don't have this indented, then my iteration of a is occurring outside of the loop. And in fact, this will create what's called an infinite loop because this condition is now always true. The a is 2, and so 2 is less than 5, so it will print 2 over and over and over again. It never actually updates the condition because I don't have proper indenting, so it should just print 2 forever, and the code will never end unless I can stop the code. So let's just show you what's going on. Like if I print this, you'll see lots of 2's, and so I'll try to stop it there. There we go. I had to force a stop of this, and you can just see it printed a ridiculous number of 2's. And that's, of course, not what we want to do. I mean, look at all these 2's. What was the point of that? That's what happens when you have an infinite loop. So I'm just going to go ahead and scroll up all the way on the side. Oh, my goodness. There we go. So we'll go back to what we want, which is with that indenting right there. And now I will run that again, and we print a 2, 3, 4, which is what the original intent was with that code. Now, some key points. We often use while loops for iterative methods when we are unsure exactly how many iterations a process should take. For example, a fixed point or a root finding method in computational math or in data science where you're doing some sort of optimization which is what's going on a lot of times when you're training a model. You don't necessarily know how many iterations you should take to actually achieve what you want in the code. So in that case, while loops are really useful. but you have to be careful about making sure the condition becomes false at some point, because otherwise you can have an infinite loop, and that's not good. Your code will never terminate. So to avoid infinite loops, it's fairly common practice to include some type of counter which tracks the number of iterations and negates the condition if the counter is ever reached, or specifies some like reaches some like maximum value, maximum number of iterations that you've kind of a priori defined. The idea would be, I don't know how many iterations this should take, but I know that I don't want it to take more than maybe 10 or 1,000 or 1,000,000. And if it's taking that long, just stop. Like, just stop the code, and you maybe need to reassess how you're trying to solve the problem. So that just is a way to avoid an infinite loop. You don't necessarily know how many iterations to take, but you know a maximum number you don't want to take. You can also exit from any for or while loop early by using a break command to exit the innermost loop. And I'm saying innermost because you could nest loops. You might have a while loop within a while loop that's within a for loop. And wherever the break occurs in terms of the indenting, so kind of which of these loops is it associated with, if that break is ever encountered in the code, because it might not be, it might be something that's only encountered if certain conditions are met, because you might be checking things with logic. But as soon as that break is encountered, it exits the innermost loop that saw that break. If you also want to stop a current iteration but continue looping, meaning that something's happened and you just want to go to the next iteration, you don't really want to execute the remaining part of the code that was in the loop, you just want to go to the next iteration, you can use a continue command, and that will immediately take you to the next iteration, skipping over any remaining code in that loop. I think this is best seen by some examples, which I have some simple ones down below. So here's an example of a counter used to avoid an infinite loop. So I usually just say count, like a variable count. It's very clear what it's meant to be here. I'm setting it equal to 0, and here I'm creating while true. I'm actually taking just a Boolean true. So this is always true. This is a condition that is just true. So this would produce an infinite loop if I wasn't careful in how I did the rest of the code. And you'll see what I'm doing is I'm adding 1 to the count each time. I'm just printing something, around and around we go, and will this ever stop? It's not even really a question. But if the count is greater than 10, I then have a break command. So it's going to break out of the innermost loop. Well, there's only one loop, so it's going to break out of this while loop. So you'll see this should print a number of times, but as soon as count is greater than 10, it should break. And we can see this, so if I run this, you'll see it ran, but it did stop. It ended eventually. And if you wanted to check actually what count was at this point, you could go ahead. I think this is maybe a good time to insert, let's say, a scratch code cell. And if I just print what count was at this point, you'll see it's 11. So when I go back to the notebook and I look at this, you see that's exactly right, because as soon as count reaches 11, it's greater than 10, and it would break. So this printed a number of times until count was 11. It was greater than 10. Another way to use a counter, which is probably a bit more common, this is how I would normally do it rather than using it with break. That was just kind of an illustration of how to use break as well, is I would create my counter. In this case, count is 0 again. And maybe I have my condition that could potentially be true longer than I want it to be. In this case, it's always true. And I want my count to be less than or equal to 10 in this case. So this is just something that's kind of logically equivalent to what I was just showing, but it's a lot less code. I mean, if you look at this, I don't have to write this. I'm writing it in less lines. I'm just absorbing that concept into my condition. So if the count if it's greater than 10, so as soon as it's 11, then this condition will become false. So true and false is false. And oh, I'm looking at the wrong code cell. Well, that's what's happening here, but I was also doing it down below. Excuse me. So let me just go ahead and run this, and you'll see that it printed again. It printed in this case, the same number of times as it would above. However, I didn't have a break command. I just had this and command in order to break it. And I'm doing the same thing here, except this example is also showing continue. So here what I'm doing is I'm adding 1 to the count each time. So I know that this will end, right? This will break as soon as the count is 11, because this condition will be false, and true and false is false. If this was an or, that would be a problem. That would again produce potentially an infinite loop. In this case, it definitely would, because that's always true. But as soon as the count is greater than 5, I'm going to start printing something else saying we are at least half done. And then this continue command will just go immediately to the next iteration, meaning that this next line of code will not execute as soon as the count is greater than 5, because I just continue to the next iteration. I don't continue with the rest of the code in that loop. I just go straight to the next iteration. So you'll see that this part, right, count is not greater than 5 until count is 6. So this won't be entered into until count is 6. So this part of the code, this print statement, will not execute for like the first half of the iterations, and we'll be printing this code. But then we will enter here, as soon as count is 6, we will print we are at least half done, and then we will continue to the next iteration, meaning we skip all the remaining code in that loop. We just go to the next iteration. So if I run that, this is exactly what you see. We are not yet halfway done is printed about half the time, and then we are at least halfway done is printed again about half the time. So that's it. That's how that's kind of working right there. And I'm going to follow up with a mathematical example, but I'm going to do that in the next section of the video, because this is a part where I highly recommend you pause, play with this code yourself, and even try your own very simple examples with some conditions and while loops and breaks and continues. We now consider a mathematical example where we are trying to iterate this following equation. This is the type of logistic equation. And what we're trying to do is find a fixed point. We would like to iterate this basically given a point x. We say the nth estimate of the fixed point is xn. And the next one is x sub n plus 1 found in this way. We take a times x sub n times 1 minus x sub n. And the idea is that we want to iterate this until the difference between successive estimates, successive points, xn plus 1 and xn, are less than some tolerance. So we have some tolerance parameter that as soon as that's reached, we want to exit the while loop. But we don't know how long, right, that will take. We don't know how many iterations there are. So we set a maximum number of iterations. Now we're going to use NumPy here just because it has this nice floating point absolute value function, which is just a very fast absolute value function. But I'm also going to use NumPy arrays later in the lecture. So I'm going to go ahead and import NumPy now. And then all of these are just variables. It doesn't actually really matter what we're assigning this in terms of the concept of what we're trying to get at. But I'm just setting a to be 2. I'm setting my initial estimate, what I'm calling x new, to be 0.49. This is my initial guess of the fixed point. I'm setting a tolerance to be 1 e to the negative 8. So as soon as that tolerance is reached, I want to break out of the while loop. So you can just see within the while loop, if we look at this, I'm just doing some iteration here. This part doesn't really matter. And I have a counter that counts until I have a maximum number of iteration, that's 8 reached. And as soon as that's the case, I just stop. I don't want to iterate anymore. And then what I'm checking is the difference between my new and my old guesses, my new estimates of what this fixed point are they greater than the tolerance? If they are, I can just continue to the next iteration. You can comment this out to see what happens. Now, this is a perfect example of where you might use continue, because if you're writing your own code, you might want to have outputs that are printed to the user that are telling them information about what's going on in each iteration. But when you're just debugging and testing your code, you might get really annoyed seeing all of this stuff printed to the screen, but you want it in your code. And so what you might do is while you're debugging and working on things, put a continue statement somewhere. So you say, look, I want all this stuff to print when other people use it, but right now I'm just trying to fix my code, get it to work. So I just want to continue to the next iteration just to check that things are working. And then when you're done, you might comment it out or just delete it. And then all this other stuff would execute if the difference in these things wasn't greater than some tolerance. And then as soon as I reach basically my tolerance, so as soon as this is not true, which would mean that x new minus x old is less than or equal to my tolerance, that would go to the else condition. And at that point I break, which means I leave the while loop. Then I have this lack of indenting, so this is not in the loop. And what I do is I print a blank line. And then I say what the iteration number was that was needed to get the current new estimate of my fixed point that was updated from my original estimate. So this is my fixed point. Really, it's an estimate. I should say this here. The fixed point estimate is equal to whatever this is after so many iterations. And notice I'm subtracting 1 here because I'm just immediately iterating. I'm doing +1 at the beginning. So my first iteration, this is iteration 1, and so this is making this a 2 in the first iteration. But if I break, then after my first iteration, I want that to be 1. That's it. I'm not really going to go over the math for this right now. This is just an example of a mathematical problem where you could use code like this to do the fixed point iteration. But I just want you to see how this works. So I'm going to run this now, and you can see that it exited after 4 iterations. Okay, so iteration was 1, and it went through this 4 times. And then it said, look, the fixed point estimate is 0.5. And so you could say like, oh, that's actually pretty good if you think about this problem. My A was 2, and so I have 2 times basically x times 1 minus x. And I'm looking for a value of x over here, or let's say a value here that gives me the same value. Like I want this number, that xn, and that xn plus 1 to agree. That's what's going on in the fixed point problem. So 2 times 0.5 is 1, and 1 minus 0.5 is 0.5. So 1 times 0.5 is 0.5. That's exactly right. That's the number I'm after, is 0.5. And starting at 0.49, I was able to get there in 4 iterations, and I really nailed it. I got what the fixed point was. If my tolerance is basically 10 to the negative 8th power. That's what this means. So you could play with this. This is actually kind of rounding what this is, this x nu. It's not going to be, I don't think it's exactly 0.5. It might be, but let's go ahead and do like, let's say 0.45. Let's start farther away from 0.5. And if we run this, now you see, okay, at 4 iterations, so it did actually, it's 0.49999, there's a whole bunch, and then there's this 4 at the end. So that is definitely within 10 to the negative 8th. I mean, if you're definitely within 8 decimal places of 0.5, and it's actually not so much that it's within 8 decimal places of 0.5, it's within 8 decimal places of the previous estimate after 4 iterations. If I want to make this really small, like let's say 10 to the negative 15th, and I run this, now it takes just one more iteration. It takes 5 iterations to get that estimate. That was with that x nu being 0.45. If I made it 0.4, I run it, takes 6 iterations, but hey, now it got it again at 0.5. That's really nice. So you can play around with these a little bit. I wouldn't change things too drastically from what I had here. But this is, again, just to illustrate where in a real practical problem, if you'd wanted to know the fixed point of this problem, which there's reasons why you might want to know fixed points. I'm not going to get into them in this video. But you might do a while loop because you don't know how many iterations it will take to get within the tolerance because you don't really know necessarily the quality of your initial guess. And maybe you want to play with the tolerance and you don't know how many iterations it'll take, but maybe you say, I don't want to take more than 8, or maybe I don't want to take more than 80 or 100. And here you're finding, I've shown you examples now where it took 4, 5, and 6. It took different amounts of iterations each time to reach the tolerance to give me this estimate. So I just don't know a priori before I do this how many iterations I'm going to take. And that's the type of problem where you want to use a while loop. But you want to generally set a maximum number of iterations and at least have some sort of condition where you break out of the loop, if nothing else. You just want to avoid infinite loops. Those can be a problem. We now move on to for loops. But before we really discuss for loops, we're going to have to define a few terms. We're going to have to define what an iterable is. Now, an iterable is an object that can be looped over. Okay, that maybe doesn't sound very helpful. What types of objects can be looped over? Well, a list, a string, a dictionary, a tuple, a range object, something we've seen before. In NumPy arrays, these are all examples of iterable objects. And you might ask, well, how can I tell if an object is iterable? The object will possess a special method called iter with 2 underscores on either side of it. So if you wanted to check if an object has this special method, you can simply scan over all the methods attached to the object by viewing a list of all the methods. But how do we get this list? Well, we can use the dir function. And that returns a list of all the attributes associated with an object. We show this in the code below. But it's really a bad idea to try to do this and scan it visually because there's a lot of objects attached, a lot of attributes attached to methods, a lot of attributes attached to every object. So it's really easy to miss it if you're just looking for it. And I'll just give you an idea of how to do this. So what we're going to do is instead use this in command, in, to check if basically what we're looking for is in the list. It's really useful. It just returns a Boolean, true or false, if it's in the list or not. So let's just go ahead and look at this example. I'm going to create a list. Remember, a list is a very flexible thing. I'm going to create this list that has an int, a string, and a float. I'm going to run it, and now I have this list. It has 3 things in it. And now I'm going to show you this insane number of things, the same number of attributes that are associated with my list. So when I run this code, here you go. Here is the list that has basically all these methods attached to it. Now you can see right here, it has the, or just, that wrong one. See, I even picked the wrong one. It has that iter thing for being an iterable object. So this is what we're looking for. Okay, well that means that it is an iterable. It's an object that can be looped over. But a better way to check that, rather than just looking at this and hoping you see the basic thing you're looking for, is just take it. Notice these are all strings. So it's you give it the name, which is a string. The name of the method that you're after is a string. You want to see if it's in that list. If I run this, it just says true. That's way better and much more reliable than just printing everything out and looking for it visually. So that's the way I highly recommend checking. If you're ever curious if an object is iterable, just give the name iter with 2 underscores. It's very important. It's 2 underscores. That's what we're there. With it's a string, so it's the name of the function, the method that you're looking for. So just make sure you have the tick mark on either side, and you just check if it's in, and then you have that dir function, and give the name of the object you're after. Now, is an integer an iterable object, right? I didn't say it was. So if I look at, again, this dir, here's another way to do this, by the way. This dir function is also an attribute that's attached to this. You can see that, by the way, here. That dir is there, and because it's a method, it's a function, that means if I want to run it, I have to have those parentheses, right? For functions require you to use those parentheses. This is just another way of doing this, dir of my int, but I'm just showing you multiple ways to do things. And again, you can print this out and go, my goodness, there's a lot of things associated, a lot of attributes associated with an integer, right? It has probably more than what you see with my list. Yeah, I think so. But what do I really look for? I'm looking for the iter, right, with the 2 underscores, this iter. And is that in there? No, it is not. That is a false. So that's not in there. What about a range object, right? If we create a range, that's range 1 to 10, and we've seen that this is a type of range, right? It has its own data type. And if we look to see if that's an iterable object, we see that that's true. So what does that mean? Well, we can make an iterator from the iterable object. That's what we can do. So I'm going to print this to you here. So my list iter, I'm going back to my list, and I'm having that iter function, that iterator function, basically. I'm passing it nothing. I'm just using those 2 parentheses, and I'm printing it. It's a list iterator object now. And so this is the thing that you're after. This is now what you can use to go basically iterate through the iterable. And a better way to do this, though, just like the dir, is just use iter to make the iterator. And I'll just do that here. And that's the same thing. It's making a list iterator object, but because I reran it, it's just storing it in, I believe, some different location memory. In fact, it is, right? I see that 7 there and that 2. Otherwise, it looked very remarkably similar this one time I happened to run it. So it is now possible, once you have the iterator, it is possible to access the elements in the iterable object by using the next function applied to the iterator. So what I'm going to show you is I'm just creating this temporary variable. I'm just going to keep assigning it the next thing in my iterator. And I'm going to print what that variable is as well as its type. And so I'm going to do this 3 times because my list object had 3 things in it. And so you'll see it prints 1, the int, the first object that was in it, 1, the string, right, the second thing that was in it, and it's printing 1.0, the last thing that was in it. So as you can iterate through, as you basically call next over and over and over again, you're just getting the next thing in your iterable object using your iterator. And I know that can seem really confusing. But the great thing is you don't really need to know a lot of this. I'm giving you more information than you actually need to know to write a for loop, but it's nice to know what's going on with the for loop. Now remember, I said a string is also an iterable object. So here's my string, what the, and I'm going to check, is the iter function in the list of attributes for this, and it is, it's true. So now what the, if I look at this, this has 4 characters. The space is a character. So you'll see I printed I have 8 print statements with this next command here. And when I print it, I see what the printed vertically. You can say, well, what happens if we try to print just one more, right? Because the E was the last thing in my iterable object. So can I get what's next? What's next after the last thing? Here's what's next. A stop iteration error. I got an error, a stop iteration. And the reason I'm showing you this is because before we go to for loops, I want you to understand that a for loop is essentially just a while loop that uses a try and except command, which is something you just saw in your Part B homework to Module 2. And what it's doing within that while loop is it's just breaking. So here's basically what's going on. If I make my iterator from my iterable, then a for loop that was basically, let's say, wrapped around this print command, it would be interpreted as this type of while loop. While true, try to print the next thing. That would be like if I try to put all of this inside of a loop. And then as soon as it's going to try it. But when it gets to the end of my iterable object, I'm going to see this stop iteration error. So if that's what I see, I break out of the while loop. This is effectively, logically, what's going on inside of a for loop. So there we go. See that if you look at this, that's exactly what happened when I printed all these. But you imagine, like, wow, rather than write that out each time, that's something that should be put inside of a loop. And you would think of a for loop for each of the characters in this string, just print that character. And if you wrote that out as a for loop, logically, this is what's going on. Like in the code, it's just interpreting it as a while loop with a try and except command, a try and except statement where it accepts for a stop iteration error, and then it just breaks out of the while loop. So this is just helping. The reason I'm showing this is it's kind of tying it together that while and for loops are really not that different at the level of how the code views them. Even though programmatically, like stylistically and syntactically, they look very different, they are really one and the same thing kind of at a logical level. So the next part of the video will actually go over specifically for loops, which are usually the things that we write in a lot of scientific code when we have an iterable object that we specifically want to iterate over. The for loop syntax is actually quite simple. You'll write something like for, and then you'll have a variable name in some iterable object. And what that does is it creates the iterator, and it's just going to pull off the next thing in your iterable object, and then you can just use it in that code, in the code that you want to do. Make sure you have the indenting, make sure you have the colon, and then exit the indenting for whatever you want to continue in the code. So for example, like with a tuple, like this is what the code would look like, and I'm just writing it here because maybe you want to play with and change the code that I have. But if you were going to have for, let's say, a string, but you could have it anything like word, you could call that whatever. In fact, I'm going to change that here. I'm going to make this word. For the word that we have in that, we're going to just print the word. So it's just going to loop through each of the objects in this iterable object. Now you could say, well, geez, I just saw that strings were also iterable objects. Now here I'm printing the word, but I could print the word, and I could also for the letter in the word, because the word itself is a string, right? Each of these is just the alpha, the Romeo, and so on. I could then print the letter, right? So now I have this nested for loop, and so you could see I have alpha, ALPHA, Romeo, ROMO. You can just see what it's doing, right? It's just for each of the words. I then can also have this nested loop, and it's because each of these words is a string, and a string is an iterable object. So I'm just doing that just to show you that even if your iterable object has objects that are themselves iterable, you don't necessarily need to loop over them. You can just be using them as entire objects. So like when it's like this, again, it'll just print, that'll be more simple, Alpha, Romeo, Sailor, Foxtrot. And I'll just go ahead and turn these back to strings, just so it looks just like what I had there. But feel free to play with that. Now, remember my string variable, which was the what the? It just is kind of this incomplete statement, fill in the blank, what the? Here it is, what the? And you could compare this. This is a very nice syntax, a very simple syntax, compared to what we had to write here, which was just logically it's the same thing. This is basically what's going on when I execute that for code. Like what Python's thinking and how it's working through it. It's doing something like this in the background. You don't see that. You just see the code you write here, but I'm just telling you kind of in the background, something like this is going on. So you can just compare that and you can just say, well, geez, you know, writing a for loop looks a lot nicer than writing a while loop using an iterator. I'd rather write a for loop if I know exactly what I want to iterate on. And I definitely recommend that. If you have something you want to iterate over and you specifically say this is the exact object I want to iterate over, write a for loop. If you're unsure how many iterations you need to take, write a while loop. And you could always just write while loops, but again, not recommended. It's too easy to write them incorrectly, make infinite loops. The for loops are kind of very safe. It's hard to write an infinite for loop. The only way you can do that is if you create your own object, generally, that has an iterator on it, that's an iterable object, and the way it iterates is it produces an infinite set of things that never ends. And that can happen if you're doing like a brute force, like password hacker, or some sort of other type of object that you're creating. Or for some other code purpose where you say, I just want to keep checking, you know, maybe like if every number was, or all the integers are prime and the integers never end, so I just want to keep going forever, and you're just letting your computer, I guess, run till the end of time or till it breaks, which is what's going to happen eventually. I guess that's fine. I just wouldn't do it. You can do it. You can. I'm just saying it's possible to write a for loop that's infinite. You just have to kind of specifically do it. You really have to be pathological in your construction or very intentional in your construction to write an infinite for loop, whereas you can unintentionally write an infinite loop, an infinite while loop. So that's it. I don't want to say more about that on the comparison of for or while loop, but I will show some examples below. I'll go over some key points first, and then some more examples, and then instructor-led activity, and that will almost be it for this video before we get to list comprehensions. Here I'm showing just a simple mathematical example involving a partial sum for a geometric series. So this is something where I'm going to sum up from little n equals 0 to capital N. This notation, this capital sigma, this Greek letter sigma, is a summation notation. The way it's interpreted, when you have this term 2 to the negative n written here, n is the index that you're summing over, and you're letting n equal 0 to some capital N value that is denoting where you want, you know, to end your partial sum. And this is basically what it's equal to, 2 to the 0, 2 to the negative 1, and then because it's to the negative little n there. And as soon as little n is equal to capital N, that's where you stop the sum. That's it. So if n was 20, I'd have 21 terms here, right? Because I'd have the 0 term, and then I'd also have the 20 term. So that's what I'd want. I would have all those terms, and then I would be estimating what this sum would be if I went from n equals 0 to infinity. This is a partial sum. It's not the sum of a infinite series. So that it's just a mathematical example just to show how to use a for loop. So I'm going to create my partial sum, which is 0. I'm going to incrementally add to it 2 raised to the negative n power, and I'm going to do that for n in the range 21. So that's going to basically go from 0 up to 20. Okay, and you're going to see that. And then I'm just going to also print out all the different partial sums along the way, and then the final partial sum at the end, which should also be what the final one that was printed here. So I'm just going to run it. It's a very simple few lines of code, and you can just see I'm adding this up, and you see that this partial sum, it's kind of clear what it's summing up to. If you were to go on forever, it's approaching 2. That's what the sum is for the infinite geometric series when you sum up 2 raised to the negative n power from n equals 0 to infinity. That is actually summing up to 2. And we're just estimating that with this partial sum. And you can just see I'm just printing this out at the end. Now, I could also iterate over things backwards. This is the nice thing about range. So I can go from 20, starting at 20, right? Because I didn't go to 21, right? Remember, range goes up to, but not including that last value. So it's going to go starting at 20. I want to go down to negative 1. So this is the step size, that negative 1 there. And I'm going to go down to negative 1, but not including negative 1. So this will go from 20 to 0. That's why we have to stop at negative 1 there. And now I'm just going to subtract off incrementally each of these pieces. And you can just see if you were to compare each of these to what's above, I'm just incrementally going back. And so when it was at 20, when I subtract off 2 to the negative 20, I'm actually only have the sum from 0 to 19 instead of 0 to 20. I took off now 2 to the 20 on that first iteration. And I incrementally take all of the terms off until I get to 0, the last term, right? When I take off the n equals 0 to 0, that's just 2 to the 0 power, but that's 1. And so I take that off, and then I'm left with 0 at the very end. So it's just counting backwards. Just another example of a for loop, but where you can have an iteration basically counting down. If it's a numerical value, the numerical value doesn't have to count up. It can also count down using range, and that's very common in some scientific computational math type applications. In the instructor-led activity, we're going to look at integers and their divisors. I provide a link here for a good starting point for this activity that has some code available, and there's a few ways that they go over how to check whether a number is prime or not. A positive integer, like 1, 2, 3, and so on, is prime if the only divisors of it are 1 in itself. So some examples are 1, 2. 2 is the only even prime number because 4, 6, 8, all the other even numbers have 2 as a divisor. But 1 is kind of a vacuously true prime. 1 is a prime, 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime, 9 is not a prime because 9 is divisible by 3. But 11 is a prime, 13 is a prime, 15 not a prime, and so on. But of course, me just saying this isn't really useful, and you'd like to have maybe some sort of code that can just check if a number is prime. Prime numbers are actually very critical in a lot of different computational settings. For instance, in cryptography, they're very important. So they have some really good applications in computer science, and specifically in cryptography and in basically encryption of a lot of code and just messages and everything else. So anyways, let's just talk about what we want. In the first code cell below, we want to create a function that checks if an input is a prime integer. This code should do the following. First, it should check that x is a positive integer, and it should let the user know whether or not the correct type of variable was received. So it should do some type checking, so it should use an is instance. If x is a positive integer, then we want to determine if x is a prime number or not and output the following. If x is prime, we just want to let the user know. If it's not prime, then we want to let the user know and return a list of all the positive divisors of x that are not 1 or x. So in the code cells that follow, you should feel free to make multiple new code cells for this activity as well. Test your code on some different positive integers, try prime ones. I provide another link here. But I'm going to pause the video here. I'm going to come back with the solution and discuss it, but you should try this on your own. Know that what you want to do, especially when you look at what the code is that they're providing, is you clearly want to have some loops in here because you want to loop through numbers that are potential divisors of the number that you have. So give it a try yourself. Use this link, pause this video, really try to do this, see how far you get, but don't take a lot of time. If you can't get it in about 10 to 15 minutes, continue on with this video. So here's my solution to the problem. I created a function called prime or divisors that takes in a single parameter x, and then I check if it's not an instance of an integer and greater than 0, because I want to just check positive integers. So if either of those is not true, then this should be triggered, right? If this is true and this is true, then everything's fine. I should go on with the code. But if either of those is not true, so that's what I'm doing here. I put all the things I want to be true together with an and then I put the not over it. So as soon as one of them is not true, it triggers this condition to be true, and it says this function expects the input to be a positive integer. And actually, at that point, I should actually return. I should just return nothing. It should. So there we go. I have that return, because otherwise it will continue to try to run with the code and it will potentially encounter errors. I then create an empty list of divisors to which I append each potential divisor. Now, if x is 1, then I already know that I wanted to return just not a prime. Like 1 is a prime, and I don't need to check anything else. It's the smallest prime. I don't need to check to see if anything divides into it, so I'll just skip everything. But if x is greater than 1, then I'm going to start from 2 up to I want to go to half the value of it, because I want to return the divisors that are not 1 or the value of x itself. So I'm going to go up to the half, and this is doing floor division, as you might recall, that 2 divide sign. So if x was like 10, this would be 5. But I have to add 1 to it because the range goes up to but not including that last value. So if I want to go to 5, because x was 10, I actually need this value to be 6. So that's something you just have to know about Python and the code you're using. Sometimes you have to make some adjustments that you kind of go, wow, why is the code adding 1 there? It's because otherwise I'm not going to check all the potential divisors. This is modular division. This is just to see what the remainder is of dividing I into x. So for each of the values I that are in this iterable object, this range, I'm going to systematically then divide each of those i's into x modularly. I'm just going to check the remainder. If the remainder is 0, that means I divides into x. I then append that value to the divisor list, which started empty. That's all I do. I don't need to check past half the value of x. That's just pointless. I can't multiply any integer by a value that's greater than half the value of x and then return x. So, except for multiplying by 1. So then if the length of my divisors is 0, so if it's an empty list, right? So I'm using things that we saw in Module 2, by the way, in the first homework with length and list and appending and everything. So if the length of the divisors is 0, meaning it's an empty list, then that means I found a prime number. X was a prime number, and then I just return nothing. I just let the user know I found a prime number. Otherwise, else, X is not a prime number, and I want to then return the divisors, the divisors list. So this is what I have. So let's go ahead and run that code. Now I can check prime or divisors, and now I can check. Let's say 10. 10 is not prime, and the divisors from 10 that are not 1 or 10 itself, just other things that are not making it prime, are in fact 2 and 5. If I looked at something, let's say like 24, then you see that 2, 3, 4, 6, 8, and 12 all divide into 24. That's great. What about 23? 23 is prime. So you could go through and play around with this, give it other numbers and see how it works. It also is useful for your activity that I'm asking you to do. But that's kind of what I'm doing here. I think I have a different type of function that I used here in an older video that I refer to when I'm doing this solution one that's posted on Canvas, or that's also in the playlist on YouTube. So that's kind of it for loops. Some other things that you might want to try, though, that I do want to encourage you to do is maybe make a new function, primer divisors list, or primer divisors array. Array would be even better, where x is a numpy array of ints. And you could check if the data type of the numpy array is of type int, like that you had the right data type for that. So if you gave it an array of integers, and so that they're all integers and that they're all positive integers, so you might have to loop through and check that like all the different values are positive, then can it run and do this where it creates like a list of lists. So you'd start with an empty list, and then you would make a list of lists for each of the different inputs of that array to check, because then you would be looping over this code as well. Or you could even try to just loop loop over all of that and just check each thing individually. It's kind of how it depends how you want to do it. There's some more elegant solutions than others. Highly encourage you to try that. If you can do that, you really, I think, are getting this down in terms of playing with loops and everything. But that's it for really what I want to talk about as far as for loops and these examples. But I am going to have some additional things talked about in the very last part of this video involving list comprehensions. This is just a brief note on list comprehensions and our first introduction to lambda functions, which is something we'll see a lot more of later on in this course, especially in Module 4. So we mentioned list comprehensions briefly in the first lecture notebook of Module 2, the Part A lecture notebook. The basic idea is to use a function or rule written within the list declaration, basically how you're casting the thing to make a list, to quickly construct the list by looping over some particular inputs. The code cells below highlight the basic ideas using an example from the official documentation. So here's a very clunky way of constructing a list. So imagine I create an empty list of squares. I'm going to fix up my commenting here because I don't like my formatting. It's kind of the old way I used to do it. And then for x in range 10, I'm going to append to the list x squared. So then if I look at this and I print the squares, this is, up to but not including 10. So I'm squaring from 0 up to 9, all the integers, and you see 0, 1, 4, 9, 16, 25, 36, 49, 64, 81. All of those numbers squared. But I had to write, this for loop to do this. At least that's the way I'm showing. But you don't have to do that. There's a slicker way of doing this using a list comprehension. So you can just, in the list, like basically with these square brackets, you can write x squared for x in range. And then that will cast that as a list. It's kind of like what we saw with in the homework 2 part A. There was some version of this going on there as well, where I was casting things as lists as well. So you might go look back at that for another example. But imagine we have a very explicit function that carries out a complicated operation, right? So this just showed you very simply how to put that for loop kind of directly into casting things as a list inside those square brackets. But imagine you had a more explicit function that was, mathematically defined as a complicated function. So here's like my complicated function, which isn't that complicated. It's just a polynomial. It's a 5th order polynomial. But the idea was that it transforms some input data x into a useful output data y. So we can use this in a list comprehension as well. So if I create my user-defined function here, and I'll just go ahead and run that code cell, and then I had a list of x values, right? So here I have 0, 5, -3, 10, and 15. And then I wanted to get a list of y values, because maybe I want to use these together to do plots or something. Well, then I can just say my complicated function of x, which is just basically what I'm doing here. This is a simple function. It's just x squared. This is my user-defined function. And I can just say for x in my x values, because my x values is a list and that's an iterable object. And so if I do this, it will evaluate that polynomial at each of those and return it into the my y values. And that's exactly what it does here, right? And these are, some of these don't look so complicated, -3, but other ones, like, boy, I wouldn't have done that in my head to get these other numbers. So there was nothing really that complicated about that function above. It's just a polynomial. It is simple enough to be defined by a single line of code. In fact, we could have just also written, like, instead of me writing my complicated function of x, I could have written that code just like I wrote x squared here in this line of code. I could have put this polynomial directly right here. I could have done that and it would have done the same thing. I never would have actually had to declare like this y value at all, like done any of this. So you could say, okay, so is there a more elegant way to do this even? Sure. When that happens, we can use what are called lambda functions. And my favorite quote about lambda functions is this: unlike lambda functions in other languages, if you've seen them, if you've encountered them in other programming languages that you might happen to know, where they add functionality, Python lambdas are simply a shorthand notation if you're too lazy to define a function. Functions are already first-class objects in Python and can be declared in a local scope. Therefore, the only advantage of using a lambda instead of a locally defined function is that you don't need to invent a name for the function. But that's just a local variable to which the function object, which is exactly the same type of object that a lambda expression yields, is assigned. So, okay, what does that all mean? Basically, it comes down to this. If you just wanted the computation x to the 5th minus 2x squared plus x minus 3 for a little bit of time in a very localized area of code, then you might as well just be lazy about it and define a lambda function. And I am showing two different ways, like, because we don't even need to define f at all. But if you might say, like, well, I want to use this function a few times, assign it a variable. Assign it a variable like f, and then it's just in that piece of code where this is defined, you have like f of x being used. But you might just overwrite f different times, like maybe you have different ways, different things where you want to use f because you're just using it very specifically, and there's no reason to call it like, my first polynomial or my second polynomial. You might just say, I only need this polynomial for this very brief period of time and maybe a few more lines of code. Give it the variable f and use it, and then you can, later in the code overwrite f with some other lambda function if you needed to use it. But my point is just, this is another way to create that same list, and this is a lambda function, very simple thing. But you don't even need to do that at all. You could have also done this, just make this lambda function, put it in parentheses, and you're basically evaluating that object, that lambda function at x. So that's what's going on for, again, x and x values. So here I don't even need to define f at all. However, I would kind of argue this is a little bit more readable than this. But that's kind of my matter of taste. That's quite simply the case that you don't have to do either one. There's no right or wrong way. It's just sometimes a matter of taste, and readability should factor into how you do things. But my point is, again, you can redefine f however you want. Like with this one right here, it doesn't really matter, and you could define it an integer or whatever. It's kind of a throwaway that you're doing at some point in the code where you just want to have like a nice easy thing to write. It makes your code very readable. Like if I make f here and I had to use it like in the next 3 lines of code and then I didn't need it anywhere else, I would probably do something like this with this lambda function. So there's no real reason to do this other than it's just, if you're a little lazy. I'm kind of lazy sometimes when I'm doing things. It is convenient. And we will encounter this in the next set of lecture notes, module 4. So we're not really going to dwell on it further here. But I am going to show here like how you can use a lambda function to help make code look less clunky. So again, readability is a big thing with code. You want your code to make sense. So imagine here, like I create my other complicated function. So this looks a little more complicated. It's not a polynomial. I'm taking sine of x and e to the -2 times x, and then I'm returning what that value is. Now, imagine that what I want to feed into this is a composition of functions. Like imagine what I actually want to do for my y values is I want to evaluate this new other complicated function at the outputs of my previous complicated function. So it's a composition of functions. Now, you could write that in here, but it starts to get a little long. It's, again, nice to just write something like a lambda function, which is just this nice, easily defined thing that does evaluate the composition of the two functions. It takes my other complicated function and feeds into it my original complicated function, that 5th order polynomial evaluated at x. So now this f is just this nice composition. I never have to define formally this other function called the composition function or some other name I might give it to do it. It's just this, if I just need this composition function in one or a few lines of code, a lambda function is a really nice way to just combine functions that you're using in a very specific type of way for a brief period of time in code. So if I do this, of course, I'll just get some weird values. I mean, look at these. I would have never guessed that those were the outputs. But that's, again, just another way where I could use a lambda function to just make my code kind of readable. And if you look at the lambda function, you see what's going on. You're saying lambda x, there's this notation. This is kind of the equivalent of defining something as a function of x, and then that colon that you see kind of here. But then you just have whatever the operations are on x that follow that colon. That's it. We're not going to dwell on this. We're going to get into lambda functions a bit more in module 4 because they're just nice when you want to just test a lot of very simple functions that you don't really want to bother giving names to. But that's it. That's it for the Part B lecture notebook. Thanks for listening.